Next, third order model with two-tone input. So now what we're going to do is look at what happens when we have two tones applied as opposed to simply one tone. So here's our third order model. Here is the input now. We have two tones, one at a frequency of omega 1, the other one at a frequency of omega 2, and their magnitudes are A1 and A2 respectively. When we do that, we have an explosion of terms, all at different frequencies. Here I'm just going to list a few of them which are of greatest importance for various reasons. In your book you can find a table that actually has all the terms in it, just for this one particular case. So what we see is we get the fundamental, and here there are two fundamentals because we have two input signals, and if everything were perfectly linear we would get two tones out. So we refer to the two tones, omega 1 and omega 2, in the output as the fundamentals. And you see that the magnitude of the fundamentals is given by this relatively complex expression, which is a function of A1, as it must be, but also A2 and also A3. So all the coefficients get involved here. We have these things referred to here as IM3. IM3 is shorthand for the term third order intermodulation. And what intermodulation is a combination of frequencies. So we see one third order intermodulation product which has a frequency of 2 omega 2 minus omega 1. We see another one that's at 2 omega 1 minus omega 2. We also see that there is a second order intermodulation product which is omega 2 minus omega 1. And again, there are many more terms that we get out of this. Now, third order intermodulation is typically a big concern because it is both big and close to the fundamentals. What do I mean by that? Well, if we apply two input signals, one at omega 1 and one at omega 2, we see that these two third order intermodulation products appear as shown here. Here's omega 1, here's omega 2, and then the two third order intermodulation products will appear an equal distance on either side of those two fundamentals. And the problem with this is typically we're trying to filter out spurious signals. These signals are close enough together so that it becomes hard to design filters that will exclude the third order intermodulation products. Or worse, it may turn out to be that these two signals are from a greater range of signals so that we cannot put a filter that will exclude the intermodulation products. So these third order intermodulation products turn out to be quite irritating, and they are frequently the thing that is of greatest interest because they most directly influence the selectivity and dynamic range of the receiver. Second order intermodulation is a big problem in some situations. Now when we talk about receivers, we'll talk about the issue of wideband tuning, we'll talk about direct conversion, but if you're interested in either one of those two things, then the second order intermodulation is very annoying. You'll see that if you have two frequencies which are relatively close together, omega 2 and omega 1, that the difference between them is very, very close to DC. That particular product we refer to as the beat product. It's the difference in frequencies. And I should say furthermore, we see fundamentals experience additional compression due to second and third order effects, right? The fundamental does not depend purely on the linear gain and doesn't depend purely on A3. It also depends on now on A2 when we have two sinusoids, and it's a complex function of the magnitudes also. So because third order intermodulation is such a concern in practical systems, we seek a simple way to characterize it. And a simple way to characterize it is in terms of this idea, third order intercept point. The idea is quite simple. Here's my plot of the magnitude of x, the input, magnitude of y, the output. Linear performance is a straight line, which goes like this. And what happens is that as signal level grows, the magnitude of the third order intermodulation also grows. So these intermodulation terms grow in magnitude, and at some point the intermodulation terms are as big as the fundamental. Here the output looks more or less like this, right? But by the time I get to here, the output looks like this. I start to see the third order intermodulation products, and by the time I'm here, I get a situation that looks like this. There's my fundamentals, and then here are my intermodulation products are all the same strength. And that's what we mean by intercept point. Now, of course, when this is going on, the device is also probably in compression. So the actual output of the device looks like this. So this is somewhat of a mythical point. We never actually operate here because the actual output is down here somewhere. Nevertheless, we can define this point because we can see what's going on down here. We can extrapolate up to that point. And similarly, we can see what's going on with third order intermodulation products and extrapolate up to that point. So when we compute a third order intercept point in the lab, we typically try to trace this part of the curve and extrapolate it up. And we find this part of the curve and we extrapolate it up and we figure out where the intercept is here. Whereas what's actually happening is the output is following this curve. Nevertheless, we refer to this point as the output third order intercept point. We refer to this point as the input third order intercept point, and we can see that the two are related by the linear gain. So like 1 dB compression point, the third order intercept point can be expressed in terms of voltage or current, or in terms of power if the associated impedance is clearly specified. So if we can agree on what impedances we're going to operate it on, we can express third order intercept point in terms of a power. So if we're talking about output preferred intercept point, we typically use variables such as IP sub 3 or OIP sub 3. And again, this is typically what datasheets show, but you can immediately convert this to an input referred third order intercept point. We typically use a variable IIP sub 3, and that's simply the output referred third order intercept point, and that should be a 3 there, divided by the linear gain. And that would be more relevant for receivers because the input signals are what we're concerned about with a receiver. Just to give you some perspective on what typical numbers look like here, for some common receiver applications, such as in cellular wireless telecommunications, we have standards such as GSM, CDMA, and so on. A typical third order intercept point specification for a cellular GSM receiver would be something like minus 18 dBm. For cellular CDMA, it would be something like minus 13 dBm. Typically, the range of acceptable input third order intercept point somewhere between minus 30 dBm and plus 10 dBm. Now, if we have a third order polynomial model, we can compute the third order intercept point in terms of the coefficients of that model. So again, everything I've said up to this point about third order intercept point applies generally, even if we have some device that doesn't follow the polynomial model. But if the device is describable in terms of a polynomial model, then we can compute the third order intercept point in terms of the coefficients. And it's quite simple to do. It's simply the solution to this equation, right? Here's linear gain. Here is the magnitude of a third order intermodulation product. And we can solve for that value of the input. It is simply the square root of 4/3 times the magnitude of the ratio A1 over A3. So again, we see that the third order intercept point increases with A1 with linear gain and decreases with A3. Should not be surprising to you. Does not depend on A2. Again, if the polynomial model applies, then the ratio of the third order intercept point to the 1 dB compression point can be calculated because I already had an expression for this. I just derived an expression for this. I can take the ratio and I find out that's a constant. That constant is about 3.03. And in dB, that's about plus 9.6 dB. So something very interesting happens. When the device is well characterized in terms of a third order polynomial model, it turns out that the ratio between the third order intercept point and the 1 dB compression point is about 10 dB. This is a very useful thing to know because, for one thing, it's very easy to measure the 1 dB compression point. I can do that with one tone. And if I know that, then I know the third order intercept point is simply about 10 dB higher. But again, all this depends on the third order polynomial response model being applicable. So for example, we know that common emitter amplifiers, that is amplifiers using bipolar transistor technology, are not exactly characterized by third order polynomial response models. In that case, the ratio between intercept point and 1 dB compression point is typically a little bit higher, typically 13 to 16 dB. So if you know the 1 dB compression point of a common emitter amplifier, typically you can assume that the third order intercept point is going to be somewhere between 13 and 16 dB higher. So this concept is useful for comparing amplifiers and in stage cascade analysis. This is something we'll talk about in a future lecture. Comparing amplifiers, what typically happens is we have to rely on data sheets, and the data sheets like to give quantities like 1 dB compression and third order intercept. So the merit or the value in these metrics is that they give us some quantitative way to compare amplifiers. A little bit less useful for actually designing systems, but more useful for part selection, for example. Just to further drive home the point, here's a plot which shows a survey of 271 commercially available amplifiers. It says here mimics, that's microwave monolithic integrated circuit amplifiers, but that distinction is not important here. 271 amplifiers, all evaluated the same frequency, in this case 50 megahertz, operated at the recommended bias condition specified by the manufacturer, and then we compare the 1 dB compression point to the third order intercept point. Now, if they all followed the third order polynomial response model, then the relationship between those two things would be this line right here. Because, for example, if the 1 dB compression point were 0 dBm, the third order intercept point should be plus 9.6 dBm. But what we see in fact is that the actual input IP3 is significantly greater. And it's significantly greater by somewhere between 0, there's certainly a few along this line, and maybe 5 or 6 or 7 dB greater than what you'd expect. So this is perfectly consistent with the previous statement I made that that for bipolar common emitter transistor amplifiers, the 1 dB compression point is 13 to 16 dB less than the third order intercept point typically. And just for additional information here, these diamonds represent differential amplifiers. And the reason I note those separately is that there's no particular advantage in differential topology for amplifiers in terms of this relationship between intercept point and compression point. I can do a very similar analysis with second order intermodulation. Again, here I'm reminding you about the terms that I get, and the primary concern with second order intermodulation, I'll remind you, is this beat product. I can define a second order intercept point in the exact same way I define third order intercept point. That is, as the point at which the second order intermodulation products become equal to the fundamental. That is, if I could somehow keep the amplifier linear through that process. Of course, the actual response looks like this, but I can go down here and I can compute a linear gain line, and I can go down here and compute a response line for the second order intermodulation products, and where they intersect then is the output second order intercept point, and then I have an input second order intercept point. Once again, I can describe all these things in terms of power if we can agree on the impedance. The output referred quantities are given by variables such as IP sub 2 or OIP sub 2, clarifying that's output. Again, this is typical for data sheets. For input referred quantities, I simply divide by the linear gain. And a typical variable to use there is IIP sub 2. With all these variables, it can get quite confusing, and not all manufacturers and not all researchers can agree on what variables to use for these things. So you have to be super careful to make sure you know what each of these variables means and what the author of the particular document is referring to when they use a certain variable. Now, having said that, I should point out that it's relatively rare to see second order intercept reported in data sheets, and there's a couple of reasons for that. One is that for most amplifiers, most cases where you have a device where you're concerned about linearity, the second order intercept is typically much, much greater than the third order intercept. So it's usually the third order intercept that's the problem, and the second order intercept is huge and only a problem in particular cases. And those particular cases are cases, for example, where you have very large bandwidth, or certain receiver architectures, in particular direct conversion architectures. Nevertheless, this is a fairly common source of spurious signals, so it often deserves analysis. Next, I'd like to talk about AM to PM conversion. The AM and PM we're referring to here are amplitude modulation, phase modulation. Hopefully you know that amplitude modulation is sending information by varying the amplitude of a sinusoid, whereas phase modulation is sending information by varying the phase of a sinusoid. Now here we're not talking about sending information, we're just talking about what form the signals take. Now this issue of AM to PM conversion is a problem for transmitters and very poor receivers. Now let me say why that comes about. It's because all devices, including passives, and in particular capacitors, inductors, and resistors, are nonlinear to some degree. Now this nonlinearity may not be apparent in some application, but eventually we'll hit a power level where the nonlinearity becomes apparent. So a way to see why this becomes an issue is just to consider a nonlinear capacitor. For a linear capacitor, the impedance is simply minus J divided by the square root of omega C. But if the capacitor is nonlinear, then C depends also on the input, which means that the impedance of that capacitor depends on the input, which means that the phase of the system using this capacitor will be a function of the input. So now the whole system response has a phase which is varying with the magnitude of the input. So if the magnitude of the input is high, the phase of the system has one value. If the magnitude of the input is low, the phase of the system has some other value. So what we see here is that amplitude variation at the input appears as phase variation at the output. And this is what we mean by AM to PM conversion. Now, this is normally not a problem for AM because AM is insensitive to phase shift. Normally not a problem for FM because FM is invariant to amplitude variation. It's also not a problem for digital modulations, which are constant modulus, in which the magnitude of the waveform is constant. However, there are a lot of modulations where none of those things apply. For example, many modern modulations use a scheme known as quadrature amplitude modulation, where both the phase and the amplitude convey information. And if the modulation is such that both phase and amplitude are used to convey information, then AM to PM conversion is a huge issue. I'd like to wrap up this lecture with a brief discussion of the linearity of differential devices. So just to remind you, a differential device is a device in which signals are defined differentially. In other words, I define the input signal as the difference between the voltage at some input terminal and the voltage at the other terminal, and the ground is implicit, right? The ground is not an explicit signal. And similarly at the output, I define the output signal to be the difference between the voltage here and the voltage here, hence differential. And that's in contrast to a single-ended system in which I have something that looks more like this, where one of the terminals is always tied explicitly to ground. There is a linearity advantage in being differential. Before I show you what it is, I'll just point out that there is no effect on third-order intermodulation. I've already shown you a survey of parts of amplifiers that demonstrates this. Where the difference will be is for second-order intermodulation. So let me show you why that is. It's very simple. Here, the output can be described using the polynomial response model as the sum of terms. So these terms go from 0 to infinity, assuming now actually an arbitrarily high order model. And at this terminal, the output again is described by the polynomial response model as shown here. But you know what? We have defined the actual voltage to be the difference between these two voltages. And here, this voltage is nominally the opposite in sign from this voltage. So we can rewrite this as follows here, where we end up with this coefficient -1, which is in the first term is n is 0, second term n is 1, third term n is 0, 2, and so on. So that what happens is all the even order terms cancel out. So what we see in the output of a differential device is that there are no even order terms. There are no terms which depend on A2, A4, and so on. So that gives us excellent second order linearity because the second order intermodulation requires the coefficients A2 or A4 or A6 to be non-zero. Now, of course, the benefit that we actually get here depends on the two sides being in perfect balance. In other words, this relationship really has to apply exactly. And there's always some imbalance in a differential device, so we never exactly get that. Nevertheless, differential devices offer a huge advantage in terms of second order nonlinearity. This concludes this lecture on linearity.